In this podcast, we're going to go through the physical properties of aldehydes and ketones, and we're going to talk about how the structure of aldehydes and ketones and the carbonyl in them contribute to the physical properties, and we'll do some health notes as well from the book. All right, so just like every other hydrocarbon that we've looked at, low molecular weight aldehydes and ketones are soluble in water. So when we say low molecular weight, we mean 6 carbon chains or less. These are soluble in water, but the solubility is going to decrease as your carbon chain length increases. So looking at this structure right here, we have in dipole-dipole bonds, so our oxygen is more electronegative. It is pulling those electrons closer to it, and it's taking on a slight negative charge. So in water, in a short chain molecule such as acetone, your water is able to surround completely this molecule, and you're able to get hydrogen bonding in a polar solvent. If you were to increase this molecule, you would lose solubility. So if you were to increase the chain length, you'd lose solubility. The polar carbonyl results in aldehydes and ketones having higher boiling points than ethers and hydrocarbons, but they're going to be lower boiling points in alcohols. And again, this is going to have to do with what intermolecular forces are between two molecules. So again, in a ketone or an aldehyde, you have a carbonyl that has dipole-dipole intermolecular forces. And in a hydrocarbon, you only have London dispersion forces. Okay, so we only have London dispersion forces. Those are not holding those two molecules very strongly together versus what you would see in an aldehyde where you have dipole-dipole. So that strength is a little bit stronger, and therefore notice the change in boiling points. Our boiling point almost doubles for an aldehyde. Keep in mind, though, a carbonyl has dipole-dipole intermolecular forces, whereas an alcohol has a hydroxyl group which has hydrogen bonding. And this is the strongest of the intermolecular forces, and therefore we can hold multiple molecules of alcohols together stronger. Our boiling point is going to be the highest there. A great example of a ketone that you would see in your everyday life is dihydroxyacetone. Dihydroxyacetone is also known as DHA, and this is one of the active ingredients in sunless tanning products, such as this Jergens Natural Glow Express. So this molecule, the dihydroxyacetone, is going to react with proteins in the skin, and when it reacts with those proteins, it's going to turn a brownish color. So you're going to get this brown toned skin. It's going to look like you actually tanned outside. They're not that great. It's not going to look real. Sunscreens also have ketones in them. Each of these is a molecule from a sunscreen. They have oxybenzone, which is a carbonyl attached to 2 benzene rings. Avobenzone has 2 carbonyls attached to 2 aromatics or 2 benzene rings. Remember a couple chapters ago we talked about benzene rings being an important ingredient in sunscreens that helps to block that UV radiation. All right, so let's take a look at some common aldehydes and ketones in your everyday life. If you're a nursing student, you are intimately familiar with formaldehyde. It is a substance that we use to preserve biological specimens. It's also known as methanol, and it's one of the starting materials that we use to make resins and plastics, and we have plastics everywhere. So formaldehyde is widely used in industry. Acetone is used to remove nail polish from fingernails. It's also a good solvent, a non-polar solvent to have around also if you have children and they get a hold of Sharpies and said Sharpies wind up on your furniture. That acetone will take it right off. Vanillin is another example. Vanillin is a flavoring agent that has been isolated from vanilla beans. So if you were to get vanilla extract that was not pure vanilla extract, meaning it doesn't have an actual vanilla seed in there, they would use vanillin to flavor that, and that is the flavor of vanilla. Same frickin' difference. A lot cheaper. Cinnamaldehyde is responsible for the odor of cinnamon. Geraniol is responsible for the lemony odor that we have in lemongrass, and citronellol is an aldehyde that has a lemony odor, and it's isolated from lemongrass as well, and you would find this in citronella candles as an insect repellent. All right, so amygdalin is something that we like to talk about in healthcare. Amygdalin is found in the seeds or pits of apricots and peaches and wild cherries. And this has been used as an anti-cancer drug. So you'd grind up the pits of your peaches, your apricots, and you would take those as an anti-cancer drug. So it is closely related to Laetrile, which is an anti-cancer drug, but its effectiveness has been unproven. So there have been some clinical trials involving amygdalin to see if this is an effective anti-cancer drug or not, but those have not been fruitful. So what happens when amygdalin enters your body is amygdalin is broken down by enzymes into 2 molecules of glucose. Yay, we like glucose, but it's also converted into benzaldehyde. That's not the concerning byproduct. What is concerning is you also get the formation of hydrogen cyanide, which is a toxic gas. This is not something that you want in your body. Hydrogen cyanide will indiscriminately kill cells. It doesn't actually target cancer cells. So it may appear that your cancer is going away because the hydrogen cyanide is killing cancerous cells, but it's also killing healthy cells as well. And furthermore, some patients that were in the study started to show signs of cyanide poisoning, but not cancer remission. So be careful with those at-home drugs.